Good afternoon, everyone. I hope you can hear me. Before introducing the speaker, I think I have to say something just a bit about myself first, because you are probably asking yourself, why would an environmental engineer introduce a quantum physicist, right? Well, the answer is only at Theo School. Actually, I don't feel out of place because I recognize in the audience here several other Theo School faculty who I think are far away from quantum mechanics. So, yeah, in the spirit of interdisciplinarity, we really make a whole school here. Okay, Mattias, I think it's fair to say, has dedicated his entire professional life, studies and career thereafter to quantum physics. I think with an eye on computing, quantum computing, which is a big challenge these days, as you probably have heard. He began his undergraduate studies at Middlebury, got a bachelor's degree there in physics, and while he was there, he already worked on semiconductor spin qubits. Qubits are the units of the bytes of quantum computing, whenever that really happens. And in that process, he worked in a lab at MIT, which then led him to work also in a lab at the Niels Bohr Institute, a famous birthplace of quantum mechanics in some respects, in Copenhagen, Denmark. After graduating from Middlebury, he went on to Princeton for his PhD, worked on large-scale superconducting circuits, so we're talking about circuits now, and got his PhD, stayed at Princeton with a postdoctoral fellowship called an Intelligence Community Postdoctoral Fellowship. Okay. And went on further with studies of quantum sensing, nitrogen vacancy, and to his credit, he developed a tantalum-based material platform for superconducting circuits, which is an invention itself. Did you have a patent for this?
I haven't seen any money on it, but yeah.
Yeah, it's a patent, but no money yet. But it has been widely adopted in the community. And that's getting pretty close to the topic of the Nobel Prize that was awarded in physics last year in 2025. So the most recent Nobel Prize, which is about quantum physics. Now that's what Mattias is going to be talking to us about his path and his own circuits, and that circuit that got in the Nobel Prize. And then when you read the title, the first two words are macroscopic quantum. You say that's an oxymoron because quantum is small at the microatomic scale. So how could it be on the large scales? Well, I think that's a good news, and hopefully the theme of what you are saying here, that quantum mechanics is growing up, all right, and it's getting close to tangible applications. You have the floor.
Thank you. And, on the spirit of Thayer School, interdisciplinarity, I think Benoit and I've had a few times to cross paths over the last few years, and our conversations have spanned more recently on quantum mechanics, but all over the map, mostly nonlinear dynamics. So, thanks for the opportunity to speak. I sort of volunteered myself to give this talk after this year's Nobel announcement. A little bit selfishly, I suppose, but I got very excited that this Nobel is very close to the work that's sort of foundational to my entire field. So I kind of want to use this talk as an opportunity to level set a little bit and explain the importance of this work. I think it obviously has very important implications for quantum computing, but I think it's a very fun science experiment as well. So without further ado, let's just jump right into it. So here's a quick disclaimer that there's going to be a bunch of equations I'm going to be flashing up, mostly because I can't help myself. But if you haven't seen quantum mechanics and fancy notation like this with brackets, that's okay. Just listen to the words I'm saying out of my mouth. If you have, of course, some of this may be a little bit of a review, but the later stuff hopefully gets a bit more interesting to you. Finally, if you have questions, ask. It's pretty early on in my PhD that I found that, a lot of people kind of claim to know things, and then you actually ask them the questions. And if you don't ask questions, you don't really get to understand. And you can sit back there and sort of nod your head and think you know what's going on and be confused. But I'd rather you just like raise your hand or just shout out a question so we can just snip it, you know, right at the origin. Okay, so the point of this talk is to sort of explain why the Nobel was awarded to John Clarke, Michel Devoret, and John Martinis this year in physics. So here's a quick outline of the talk. I'm going to do a really deep crash course in why we need quantum mechanics. A lot of you are very comfortable with the idea of photons and, you know, subatomic particles and that sort of thing. But I kind of want to give you a perspective of like why this came about originally. What were the sort of key signatures that gave rise to us thinking that we needed to overhaul classical physics? I have a bunch of the students in my intro quantum class here. This ought to be review for you, and I hope this is a good way to refresh what we've talked about this week. And then we'll get into Nobel, talk more broadly about superconducting circuits, and then I'm going to be talking a little bit about my work on these so-called two-level system defects, which is a big engineering challenge for the field and some of the work that we've been doing here at Dartmouth. So why do we need quantum mechanics? Well, the sort of original governing experiment that gave us a hint that there was something wrong with classical physics goes back to a very old technology, which is forging metals. So when you heat up something in a kiln to forge it into whatever shape you want, and we're talking, this is a very old technology that humans have been doing for a long time. It was pretty well understood that if you heat a metal up to a different temperature, it glows at different colors, right? We've all sit around a campfire and you know that, you know, in the early stage, once you start to get things going, all the colors of the coals are a little bit more red. But as things get really hot, you know, you want good s'mores coals, it gets a little bit whiter. That's essentially telling you that the temperature of those coals is changing. So this was a very well characterized phenomenon, and we had a good understanding of how temperature and the color that's emitted were related. Now, the big problem with this is on the right here, I have a plot of the wavelength of emitted light. The y-axis here is sort of how much energy is emitted at that wavelength. The measurements that we're talking about that were done, and we're talking about the end of the 1800s really, where we had a really careful experiment of these things. We get curves like this that are sort of peaked. A lot of, you know, at a few thousand Kelvin, you go from having things peaked in the infrared here to more in the visible. Again, think about the hot coals. This peak, as you get hotter, is shifting more towards a wider spectrum and into, you know, infrared and blue. The sort of best theory that we had at the end of the 1800s gave a prediction of this, and instead we needed this. So anyone looking at this should know that that's a terrible agreement with the data. But I want to walk through exactly how you make this argument, because I think it's kind of one of these amazing, you know, I'm talking about how to kick off the quantum revolution, and we got to get into the math just a little bit. So if I want to take this chunk of metal and I want to ask the question, how much light is emitted at different temperatures? I can make a really simple model by just saying, let's treat this thing as a box, and I'm going to ask the question, how many electromagnetic modes can I fit into this box? So each one of these modes represents the electric field of a mode that, you know, let's say we take a very small piece of this metal. I can have a bunch of different solutions to this that all have different frequencies. The only thing is I need to satisfy the wave equation, and I have my boundary conditions that the field should go to 0 at the ends of this box. So we make, well, first we need to make a relationship between what's known as the wave number, which is inversely proportional to the wavelength. The relationship between that value k and the angular frequency omega is related by the speed of light c. So if I want to count the number of modes that fit in this box of length L, I can say that n is basically 2 times the length of that box over the wavelength. And I get a relation, if I do a little bit of remajiggering, to write this number of modes in terms of the length of the box, pi, and this wave number k. And so if I think about one dimension, I can now ask the question, if I change k by a little bit, how many additional modes do I get, dn? Now, part of what I'm doing here is we want to evoke calculus. And so all I've done is taken this formula here that relates n and k and sort of written it as some little change in k and how that changes the number of modes that I count. So now the trick is that we need to extend this to 3D because this is, of course, even though it looks like a 1D box, we're talking about an actual chunk of metal that lives in the 3-dimensional world. So I've just extended this and extrapolated to 3D and added one factor of 2, which is mostly just to account for polarization. These factors of 2 and pi are not the problem with this calculation. These are more just bookkeeping, okay? So the last trick I need to do is instead of writing this as a little volume element of k, I just rewrite it in terms of a sort of, this part is a little bit more tricky, but what I want to do is express dk and dn together in the same way I did in 1D, but I need to get rid of this pesky 3-dimensional dk. And I do that by saying that I'm looking at some little dk with some surface area of a sphere. Again, these sort of details of the argument I don't want to get too hung up on, but trying to hash out that now I can write an expression for if I have a little change in omega, which is related to the frequency of the light, how many additional modes do I incur? And again, what we're doing is just trying to count the number of modes that we fit into this box as a function of omega. And the key thing here is this scales like omega squared. So as I make that omega higher, I get a lot more additional modes I can think of. One way to think about this is we have all these modes which involve different numbers of squiggles along x, y, and z. And as I make omega bigger, I can sort of exchange more wiggles along x for fewer along y, and I have a lot more ways to shuttle this energy around. Okay, this is a bit of a math exercise, but I want to kind of get to the key punchline here. So if you take on faith at the moment that this counting argument works, I'm going to sketch through the classical argument. So now, if we want to know the total energy in this little box of my metal, whether it's iron or steel or whatnot, what I need to do is calculate U, which is an energy density that's a function of the omega, which is the angular frequency. And that's saying I divide by the total volume. This gives me an energy density. And I need to calculate how much energy changes, how much additional energy I get for a change in omega. Okay, so now the trick is I've written dn in terms of d omega. This is counting the number of modes. The last thing I need to do is figure out how much energy to put into each of those modes. And once I do that, I'm done. The classical way to do this, and this was sort of state of the art at the end of the 1800s, was using the equipartition theorem, which chemists should all be familiar with. This says that if I have a degree of freedom, and I'm sitting at some temperature T, I give 1/2 kBT to each of those degrees of freedom. So classically, I can say that I have some amount of kinetic energy and some amount of potential energy, and that gives me a total amount of energy that's basically just given by kBT. So you walk through this, you plug in this expression, which says for each one of these modes, I give it a kBT's worth of energy, and I get an energy density term that goes like kBT over some factors. C squared we definitely need to be careful of. Let's not worry about the pi squared. The key thing is this should scale like omega squared. That's the classical argument, and this is the Rayleigh-Jeans law. The quantum argument, and let me back up, this formula is this. So the omega squared is causing this blow up here, and there's clearly something wrong with that. The argument of counting the number of modes is probably correct. The real thing that we should be worried about is how much energy we assign to each of those modes. Now I know this is a bit technical, but it's actually a fairly dramatic disagreement. So let's just finish this derivation here. So clearly this classical derivation fails. The solution to this is a very revolutionary restructuring how we think about the problem. And really, Planck, who, essentially this fundamental constant that we use in quantum mechanics, Planck came up with this as a bit of a math hack to kind of make this work. Essentially, he saw the blow up happening at high frequencies or low wavelength, and he said, let's try to squash that. And the sort of leap of faith was he said, maybe at some level, you actually have discrete elements to nature, like energy needs to come in finite packets, and maybe those packets of energy are proportional to wavelength. And we have some proportionality constant that essentially he said, let's play with that later and use it as a fit. The next thing is you make some sort of statistical arguments that says at some temperature, how many on average of these packets of energy do I have? Now, when you do this, you get a very different looking expression that seems to follow omega cubed. But the key thing is that this factor essentially squashes all of that blow up that's happening at that high frequency or low wavelength. This is known as Planck's law. And this does a very good job of capturing what we actually find in nature. So the takeaways of this is that we did a little bit of math, but the key idea is that Planck went out on a limb and said maybe things are sort of granular at some level, and there's some proportionality constant that I can use, and I'll tweak it until I get a good fit of this data. And that turned out to be Planck's constant. And what this tells us about reality is that energy actually just comes in discrete packets that are countable. And they have this really simple relationship between the angular frequency omega and the total energy. And then the only thing I need to do is govern the statistics of how many of those exist in my black body, given by a simple statistical argument, which is essentially given by Boltzmann's distribution. So this really kicked off quantum mechanics because it works really well, and it's a very different picture of the reality that we live in, okay? This was kind of further sort of confirmed by some experiments, again, late 1800s, looking at what happens when you shine light on different kinds of metals. So this is an experiment where they have a glass vial, they shine light on this metal plate, and they can look at different voltage biases. Physically, what happens is you shine light on this plate, and you generate electrons that get kicked off the plate, and they have some amount of kinetic energy. Now, you end up with these kind of funky curves where what we're looking at on this axis is the voltage bias on these plates. And now over on this positive voltage, what it says is you generate some negatively charged electrons, put a big positive voltage, and we're going to pull off all those electrons and we can generate a current. Now over here, what we have is we get this saturation, which is basically saying in a really big voltage bias, I pull off every single one of the electrons that gets generated. These two curves are slightly different intensities of light that I apply. And all this is saying is that if I'm pulling off every single one of those electrons, as I increase the intensity, I get more electrons. That's pretty easy to intuitively understand. The weird thing is what happens down here. And what happens down here is all of these curves eventually saturate. Now at a negative bias, you're actually saying, I'm kicking off these electrons, but I'm going to shove you back to this plate, and I'm not going to let you generate any current. That's why these curves go down to zero. But what's somewhat odd is that these curves all coalesce at the same point, no matter how much intensity I apply. And eventually what we sort of learned from this, and this was all sort of pieced together by our friend Albert Einstein in 1905 as a 26-year-old patent clerk. So working a full-time job, and he's just doing physics on the side, that if you turn this intensity really, really, really low, that these electrons still, if you generate one electron, it still has some amount of kinetic energy. Okay? And so the way to understand this is exactly, commensurate with what Planck did, is that the kinetic energy of those generated electrons is directly proportional to this h bar omega with an offset that's known as the work function of the metal. And it turns out, different metals have a different offset here. Essentially, the coalescence of these curves happens at different places. That's all in the physics of the material. The key thing is that Einstein sort of reproduced what Planck had found, that energy goes like h bar omega. And that at some level, you can think about a countable number of h bar omegas, and that physics is sort of granular at that level. Okay? So then a few years later, of course, Bohr came up with the famous Bohr's model, which was used to explain the spectra, the light that's generated by different atoms when you excite them. And now the argument here is that you have some positively charged nucleus made of, a proton or several protons, and you have an electron. Here's what's odd about this, is that if you have, a positively charged nucleus and a negatively charged electron, these things are attracted due to Coulomb's law. So you can think about a classical orbit around this proton, just like us rotating around the sun. The problem with that is, you talk to anyone that knows E&M very well, is that this electron is accelerating. And because it's accelerating, it's going to emit light. That's sort of how we generate, say, actually all forms of light is some sort of jiggling of a charged particle. All the radio signals, it's a big metal pole, and you just jiggle electrons up and down, and that's how you generate radio signals. This electron would be accelerating and therefore generating light. So you play this out as a function of time, you give the electron some kinetic energy, it spits out light continuously in this rainbow, and then the electron sticks to the nucleus, and you basically have no chemistry, no life, everything is pretty boring. So clearly that's not how things work. And what instead you see is not a continuous rainbow of emitted light when you excite an atom, but you see specific spectral lines. You take a diffraction grating and you throw light through it, you see specific resonances, not a rainbow. That's telling you that something is, again, discrete. And the Bohr model says, let's take all of the classical interactions here, but let's do one little trick, which is that we found that Planck and Einstein found that you needed to quantize energy. And Bohr said, what if we take all of the relationships between, Coulomb's force and angular centripetal force and all of that stuff, but what we do is we quantize the angular momentum that we have. Again, a very simple math hack. So this angular momentum comes in these nice units of h bar. And therefore, if you want to look at a transition between two discrete orbits of this electron, that will have some finite energy, which corresponds to the energy of the emitted light. And that is just directly related to the energy difference between these two electron states. So what I want to get at here is this is yet another very, very educated guess, but all of the three different experiments that I was talking about were very, very different from our classical understanding of the world. and all involve some sort of educated leap that then, now this is all very commonplace and we know a better way to describe this, but at sort of the turn of the 20th century, this was kind of a revolutionary new way of thinking about physics. Okay? Now, the proper way to think about it is using Schrödinger's equation, which was developed in 1925-ish. I was telling my class today, actually, that the Nobel Prize for Schrödinger was given in 1933. So 8 years is actually a pretty short runway between, like, here's my equation and here's a Nobel Prize. The Nobel I'm going to talk about today was for work in like 1984-85 and was given a Nobel this year. So I would say this is a pretty short turnaround, which should speak to the genius of Schrödinger's equation. So this is it in all of its full glory. Psi is what's known as the wave function. This is our best friend in quantum mechanics. If you want to move into a 3D picture, we just replace this second derivative with a gradient. Everything else works in a very similar way. We can, do the standard separation of variables, and most of what we're doing when we're solving Schrödinger's equation is looking for these wave function solutions. Now, this particular equation is written out in sort of a continuous manner where R is a position in space. And so the sort of mathematical machinery we use to solve Schrödinger's equation is calculus. These days, it's much more common to use this fancy notation known as Dirac notation, which actually is a very convenient mathematical tool. And the machinery that we're going to use is linear algebra. And so we can think of our eigenstate psi as being a superposition of all the possible basis states psi sub n. What I think is funny about this is engines 23, we go from engines 22, we start with a lumped element description, and then we go into a distributed model. Quantum mechanics, I actually go the opposite way, is that we start with this full sort of calculus-based description of Schrödinger's equation, and all modern practitioners of quantum mechanics use linear algebra as the bread and butter. So, both are useful tools, is all I'll say. Okay, so when you solve for the Schrödinger equation in all its glory in 3D for this atomic model that Bohr put out, and you solve it in all its glory, you get these beautiful shapes, which are known as spherical harmonics. For those of you that have studied chemistry, these should look familiar. So what I'm plotting here are the distributions of where an electron sits, say in a hydrogen atom. This is the simplest ground state where the electron is just sort of smeared out in a sphere. And you get all these beautiful shapes that correspond to different orbitals. This is sort of the full glory of solving Schrödinger's equation for the hydrogen atom that we now use today. Fun fact is, like most atomic physics, this works really well. We can solve Schrödinger's equation here, but it gets really, really nasty for any atom that you might care about. But we could talk about that another time. And so the picture here is that we just treat one of these states. They have these beautiful structure of where the electron lives. But most of the time you just say, oh, there's a state here and there's a state here. And I can apply enough energy to make a transition between those two states. And I typically don't care about the structure of the electron. I just care about a state being here at this energy and a state being here, and I can drive a transition. Okay. So I think in order to introduce this notion of macroscopic quantum coherence, we have to talk about the classic Schrödinger's cat. So now we've introduced Schrödinger's equation, and hopefully everyone's heard of Schrödinger's cat. It's the classic thought experiment where you say, I have some quantum system, say a little electron, a little atom that has two energy states like I was just talking about. And maybe, quantum mechanics says that there's a little bit of randomness of when this thing might transition from E to G. And when that happens, it generates a photon that we pick up with some detector, and that, in some really bad Rube Goldberg device sort of thing, triggers a hammer to open some cyanide, and then the cat dies. It's a really morbid example. And this is often, I find that this is often the example of like, wow, quantum mechanics is weird because Schrodinger's cat, like how can it be alive and dead at the same time? And it's actually not why Schrödinger sort of came up with this thought experiment. It's exactly the opposite. So the thought experiment says, well, maybe we can have a superposition of the atom in the excited state, so no photon emitted, and the cat's alive, and the atom transitioning to the ground state, generating a photon, and the cat is dead. And all of the funny, weird stuff about quantum measurement says, oh, wow, that's kind of crazy. You can have a cat be alive and dead at the same time. Well, this all sounds like kind of plausible, but Schrödinger actually brought this up as like, there's something weird here. And while this electron can be in a well-defined state, and I can ask the question, are you in the excited state or are you in the ground state? Are you in E or G? Can you do that with a cat? Is the cat really like a macroscopic quantum state? The answer is no. It's a lot of atoms, it's a lot of noise, it's a lot of thermal noise. This whole thought experiment actually pointed out that like there's something odd about this experiment. And if you take anything away from this talk, it's that Schrödinger's cat is not about like, oh, you can have a cat that's in a superposition of alive and dead. It's that there's something wrong with this picture. And the incorrect thing is that this cat can't be in a macroscopic quantum state. And I want to use this both to dispel a lot of like misconceptions about Schrödinger's cat, but also introduce this notion of what is a macroscopic quantum state. So what we're going to leverage a lot, and I see my friend Rufus in the back, and I'm going to call him out a bit, because if you want to know more about superconductors, go talk to Rufus. He's really the expert. But what we're going to leverage in talking about macroscopic quantum states is superconductivity. And again, talk to Rufus to talk about why this is not quite the right picture. But this is my simple picture for what superconductivity is. Normally in a material, you'll have some positively charged ionic cores, and then the electrons are these negatively charged things that move through those ionic cores, and you can have transport through, say, a metal. Superconductivity is this very interesting phenomenon where materials like this circuit here, or honestly aluminum, will superconduct below a Kelvin. These are things where if I want to know how easy it is to move electrons through this material, if I get it cold enough, you can get correlations between the electrons, and those correlations allow it to flow essentially without resistance. This is a nice little cartoon where you can think of, well, this first electron moves through and it sort of pulls the positively charged ionic cores together. And that makes this nice little path where now the electron coming in from behind feels a little bit more positive pull, and these things become correlated as they move through. There's a pretty deep analogy to what's known as a superfluid. So you take something like helium and you again cool it down to a very cold temperature. Most fluids have viscosity, but it turns out if you get certain fluids cold enough, you can have a superfluid, which is something very analogous to a superconductor, where this is trying to show actually some of the sort of foundational experiments done at Cornell. Not sure what year, maybe the 60s or something like that, where basically you have this thing of superfluid, and actually what happens is it can flow essentially without viscosity. So what it does is it just climbs up this wall and starts dripping down the side. So this is a fluid that can essentially flow without viscosity in the same way that a superconductor can flow electrons without resistance. So these are sort of related, kind of odd phenomena, okay? Again, they involve things being very cold. So now we're going to evoke some simple circuit, and I want to just go back to a classical little LC oscillator. I don't think they're still used in little wristwatches, but you can think of like a little quartz oscillator. But I'm going to call out my other colleague. Jason will tell you about how to build it. Most people know how to build these circuits. So you can have some energy stored in the electric field in a capacitor, and that discharges, and then you have the inductor that stores energy in the magnetic field, and these things just oscillate back and forth. So we can use some simple circuits to say that the voltage across this capacitor, or this inductor and capacitor, goes like minus L, and then the time derivative of I. This minus sign is just sort of a little bit of a bookkeeping of how we define the current. Similarly, we can think about the current through the capacitor as being related to the capacitance and then the time derivative of the voltage with respect to time. So what we can do here is just differentiate this equation, right? And now we get two derivatives of voltage, but then I have a di dt, and I'm going to use this formula here and substitute. And now I get a differential equation that involves two time derivatives of I, plus, 1 over root LC I equals 0. And hopefully most of the students here can see that this is solved by some nice cosine and sine functions. So all that's to say is that when you construct such a circuit like this, you get a total direct analogy to a mechanical mass on a spring, and this thing just oscillates forever. We don't have any resistance, so this is really like a lossless system for now. Okay? So another way to think about this system, and we're going to sort of take the leap of how we think about this quantum mechanically. And I'm not just doing this as like, I feel like we've done a little bit of math, but I'm not doing this as like a just circuit exercise to, I don't know. This isn't a normal class, but I'm trying to make an argument for the circuits that we eventually build, like this superconducting circuit I have here, which is really like a quantum mechanical version of these LC oscillators. And the way to do this in a quantum mechanics language is we just need to express the total energy of the system. It's a little bit like in kinematics. Once you learn that like conservation of energy is the great way to solve kinematics problems, that's sort of the way to go. So I can write now the total energy of this circuit as this nice form where I have 1/2 Li squared plus 1/2 Cv squared. So the capacitor and the inductor are on sort of equal footings, and this is an expression for the total energy of the circuit. Now, what we're going to do here is just use our circuit relationship for the inductor to rewrite V in terms of our little charge Q divided by the capacitance. And I'm going to replace the current with a variable phi that's related by the inductance L. All this is done to rewrite this total energy into what's known now as a Hamiltonian, which is basically a way to count the total energy of the circuit. But now I've expressed it in terms of this little charge Q and this variable phi, which is related to the current. Okay? Now, here's the quantum step. All I do is put funny hats on things. And that doesn't sound like a lot, but let me explain what I mean by this. When I put funny hats on things, I can rewrite this energy expression, which is currently totally classical, in terms of what are called creation and annihilation operators, which is a fancy way. All I've done is rewritten all of these variables here in terms of what are called A and A dagger. And that allows me to rewrite this Hamiltonian, which again is totally analogous to like what is the total energy of the system, in terms of these little funny A's and A daggers. Physically, what I'm doing here is I'm saying that this thing is composed of electric and magnetic fields. I know at some level quantum mechanics has to come into the play. So all I'm doing by rewriting this in creation annihilation operators is saying, I want these things to count the total number of photons in the circuit. And this expression here is telling me that h bar omega is the energy per photon. This thing basically counts the number of photons. So this relationship here says I can think about the total energy in my circuit now as just counting the number of photons in the circuit. There's one fancy thing that pops out here, which is this 1/2, which is sort of the fuzziness of quantum mechanics and a lot of good stuff, but let's not get too hung up on that, okay? So all this is to say, I found this kind of like not very satisfying at first. When I saw it, I was like, oh, we just need to quantize. So the recipe for doing quantum mechanics is you write down the classical total energy, and then you quantize it. And all that's saying is you just need to have it in a language where when I say 1 excitation, that's h bar omega of energy. That's what all this mathematical machinery is about. And then let's not dwell too much on these commutators and things like that. Okay? So now we're in a language of thinking about what are quantum harmonic oscillators. And so the language here is that we take this LC oscillator, and all this is saying is that I have the same resonance condition for the circuit, but this expression just counts the number of excitations that I have. And so I can think now about energy levels of this LC circuit as being labeled by 0, 1, 2 on up to infinity, where these numbers are just counting the number of photons in that LC circuit. And the quantum mechanics thing is that you can't have a half and weird combinations of the two. You have to have, 0, 1, 2 on up to infinity. When I ask the question, how many photons do you have? At some point it's a countable number. Okay? Now, in an experiment, what you can see from this is that if I scan over this resonant frequency, I see a peak, which is to say I can put energy into this system. This is analogous to saying that this mass has some resonance. And when I drive it on resonance, I can excite it with excitations. For the record here, Andrew Cleland was here in the fall, and all of this mathematical machinery also does explain like physical vibrations in materials, known as phonons. Sort of the vibration version of a photon. Okay? So here's where we're going to get into the superconducting circuits, is that we can actually build these things. And the way to do it is you take what's known as a coaxial cable, which is kind of like, a lot of these power cables are an actual coax. So you have a center conductor and an outer ground. A coplanar waveguide this is all ground, and then you have a center conductor here. So what you do is you take a little bite out of the center conductor, and you get reflections of that microwave frequency light that bounces back and forth for a period of time, and that means we can store microwave photons in this little cavity. And the kind of amazing thing is that we make these out of superconducting materials, and they're pretty large, actually. So this is a chip. We have many, many of these oscillators on here, and this doesn't look very large, but it's a lot larger than an atom, right? This is a 25 millimeter in length thing, and what I'm going to talk about with the Nobel is that this thing we can prove actually just behaves like a single quantum mechanical object at some level. Okay, so in reality, you end up with these little wiggles to get all the lengths right, but these little holes here are like right here and right here. And then we can make electrical connections to this, cool it down in a dilution refrigerator, and this thing will act just like a little harmonic oscillator. Kind of the simplest system. Physicists love harmonic oscillators. So do I. So this is an actual macroscopic circuit, okay? So here's the sort of caveat, is that let's say I make one of these objects, and I have one here, and this is, again, a little bit of a math aspect, but this is all just saying that I can think about the states of this thing as just what are known as Fock states, which are basically just counting the number of photons in this circuit. The problem is, if I apply a little microwave drive to this system, what I end up with is known as a coherent state. And this is a bit of math, But all that's to say that if I just start to apply microwave photons to the circuit, I don't get one at a time. I get what's known as a coherent state, which is this nasty combination of 1 photon, 2 photons, 3 photons. And it's very hard to say that things are sort of discrete when you end up mostly with coherent states. Okay, so this is hard to say that macroscopic things obey quantum mechanics when you mostly end up with these coherent states. So now we need to use one more trick, which is a very, very useful trick in superconducting circuits. So I introduced this notion of a superconductor. The beautiful thing about a superconductor is all of the energy levels get mapped down to this nice ground state, and they're very far away from the electrons acting in a resistive manner. So they're sort of gapped away from the rest of the spectrum. This is what's known as a Josephson junction, and this is kind of the really secret sauce of superconducting circuits. What we have here is a layer of metal. This is typically aluminum. This is also aluminum. And you see here what's known as a Josephson junction. And if I want to send paired up electrons from this section of superconductor to this section of superconductor, I need to go through this junction. And this junction is a small insulating layer of oxide that generally those Cooper pairs have no business going through. It's an insulator, right? You should not be able to move electrons through that thing. But what you can have is that pairs of these electrons, these Cooper pairs, can tunnel from this superconductor to this superconductor if that barrier is sufficiently small. Here's kind of a very simple way to represent this. Again, this is kind of the mathematical way. This is sort of a funny way of saying that, how do you think about a Josephson junction? Well, I can say I have m number of Cooper pairs here, and all I'm doing is I'm just sloshing those back and forth. So the more amazing thing about this, and this is part of the Nobel, is that this rate is governed by this energy scale EJ. And the kind of amazing thing is that this is something you can infer from knowing the superconducting gap really well, which is great. You just try to say, what is the resistance of this metal as I cool it down, and eventually it'll go superconducting, and you can get a good measure of this energy scale. And then it's just, what is the resistance of this junction? So it's kind of amazing that you can measure something at room temperature and know a pretty good measure of the superconducting energy, and you can predict what this is. When you read these sort of original papers that underlie the Nobel, part of what was amazing is they could characterize all the variables that they use at room temperature, and that allowed them to build a quantum model that worked pretty well. Okay? So again, a little bit more math, but what I want to get at is that we have, actually, let me just move through this quickly. Let's get to the good stuff. So this is the circuit that they used in this paper from 1985. These are the 3 Nobel laureates. You can tell, it's a little bit older. This is kind of a granular image, but what they have is they have a current bias here. They have a little capacitor, and then this X thing here is those Josephson junctions I was just talking about. So this is the circuit that they built. They can measure this voltage with a lot of precision and apply a current. The way to think about the energy of this system is that the Josephson junction has this characteristic energy scale EJ. That's this circuit element. The capacitor introduces this circuit element, which is basically, this is the total charge squared divided by the capacitance. And then this current bias gives you this term here. Now, this, if you haven't seen this kind of thing, it might not make a lot of sense before, but here is sort of the energy landscape of this circuit. So you get this kind of tilted washboard, where now if you quantize this thing and you say, what are the allowed energies of this circuit in a superconducting state, you get a handful of energy levels here that are spaced by an energy scale delta U. And the question is, how do you measure that you actually have quantized energy levels here? And the sort of amazing thing about this, and the reason why this is Nobel quality, work, is that this variable phi is actually a macroscopic quantity. So this junction separates two very large pieces of metal. And those metals, because they're in a superconducting state, I can assign one variable to that huge group of atoms. They're all hanging out in a superconducting state, and I can treat that as one macroscopic quantity that I assign to a very large piece of circuit. The key thing is that piece of circuit is just separated by the other piece of circuit by this Josephson junction. And the question is, how do I measure these energy levels? Well, there's a bit more quantum physics that shows up here, which is that when I, say, have this energy level populated, what can happen? Now, classically, we should just hang out there forever. But quantum mechanically, just like in a Josephson junction, this thing can tunnel from this little local minima over to here. And what that does is this will sort of cascade down this potential well, and I get a small voltage across that junction. So experimentally, what you do, you apply a current bias, you end up somewhere in here, eventually the system tunnels, and I get a little voltage on that circuit, and I can measure that. That's the experiment. So how do you actually do this? Well, you have to, of course, make the circuit, but there's a lot more to it as well. You obviously need to have things cold. So you need cryogenic temperatures. So these are temperatures well below Kelvin. This is from a dilution refrigerator in my lab. And I'm pretty happy with this fridge because we can get everything on this base plate to below 7 millikelvin. So that's pretty dang close to absolute zero. And that means, one, everything is superconducting. But it also means, two, that I don't have a lot of thermal energy around to just sort of populate these random states. Because the energy difference we're talking about here is in the microwave. And that's not a lot of heat, would give you enough microwave energy to sort of go from this well-defined state up this ladder. So you need cryogenic temperatures, and then a lot of the sort of art that they figured out in this is how to get the signals from room temperature. You can see one cable here, actually. You have some electronics over here. You need to send those all the way down these lines, all the way down into your circuits, and then amplify them and send them back up to room temperature. Now, room temperature is 300 Kelvin. We need to get well below 1 Kelvin. That's a huge noise difference. 300 Kelvin has tons of noise. So what you do is you actually generate a huge signal, and then you attenuate the signal as they go down the fridge, which is to say that you have a bunch of voltage dividers that sort of dump the energy and make sure that that noise floor gets way low so you don't just look at noise down here. So you need a lot of attenuation, a lot of filtering, and then you need very good amplifiers. So a lot of why this was hard in the 80s is none of this was really well understood. These days you can just buy these things. Back then you used to just like make your own cryostat, and they had to figure out how to get all the filtering right. My student Juan, we've been thinking about like how much attenuation you have at each stage and what's your effective temperature, and all of this stuff is essential to making sure that you can get everything quiet enough that you can resolve like actual energy levels of these circuits. So here's some of the data from the experiment. So what we're looking at here is essentially you do an experiment, you apply a voltage to this thing, you end up in some energy state. After a little bit of time, you'll get a macroscopic tunneling event and you measure a little voltage. The deviation of that little voltage rate compared to a baseline when you apply a microwave is what they're plotting here. So let me just sort of walk through that. The energy difference between like these various states 0 and 1 and 1 and 2 and 2 and 3 are shown here. the actual experimental data, we get this nice peak here. What does this correspond to? It says, if I apply microwaves at 2 gigahertz, I can excite a transition from this state to this state. Why is this an amplified signal? Because every time I go up this ladder, I can tunnel out much more easily. So experimentally, what you measure is that the rate at which this macroscopic kind of aggressive tunneling event happens, and I measure a voltage, that is related to which energy level you're in. This is a crucial thing because it allows you to say, like, where are we in this circuit? A slightly better way to look at it is, do you see these peaks? They move from 3.7 gigahertz to 3.4 gigahertz. That corresponds to, like, they're applying a different current bias, and that actually tunes this energy difference here. And really what's amazing is that they can see this at all. Because this is actual, evidence that we have discrete energy levels and that we can resolve those in a circuit that's a really big structure for quantum mechanics to work in. Okay? So as you increase the temperature, and the relevant thing is comparing the frequency of this thing to the kinetic energy, you go from having a nice peak to starting to see a little extra peak, which is what's happening there is you have enough thermal energy to excite you to the next energy level, and you start to see some spectral signatures of that. And then if you get high enough temperature, you lose everything. The temperature will destroy all of this, mostly because you've just given it enough kinetic energy that you don't hang out in the ground state. Okay? Are we okay with this? It's kind of fun to show these plots too, because there's all these clever like insets, these are all probably like hand drawn. And I have a lot of fun reading these old papers. Okay? So that was really the work that gave rise to the Nobel Prize. Now, it doesn't seem like a lot. The big thing that they did was it was surprising that you could have a really large object behave quantum mechanically. But why is this really a Nobel? It's because there's an entire field now that's kind of taken this physics and run with it. So here's kind of a schematic of the tools that we have to play with. Essentially, we have all the normal circuit elements. We have inductors, capacitors, but then the key thing is now leveraging these Josephson junctions. And these Josephson junctions allow you to sort of look at discrete, effectively like 2 energy level systems known as qubits. So this is basically you have 2 islands of superconductor. This thing forms a nice capacitor. And then essentially what you have here is Josephson junctions where Cooper pairs on this island can tunnel over to here and vice versa. And again, the macroscopic bit is that these things are actually huge. This is like hundreds of microns. That's very large. This thing acts like a little artificial atom. And what's amazing about this is that we can play with these parameters by how we fabricate the circuit to realize a lot of different artificial atoms, a lot of different couplings. This thing is a little antenna that we can make pretty large so we can couple really strongly to the field. It's not just superconducting qubits in quantum computing. We can also use Josephson junctions to make really, really fancy amplifiers. So these are Josephson parametric amplifiers. These particular ones are made at MIT. It's basically a transmission line with at least several hundred junctions, if not a few thousand, in a chain. And now when you pump this system, you have some incoming wave and you pump it with some other frequency, you can get amplification that is just about as little extra noise as you can possibly get from quantum mechanics. So these are things where if you put a few photons in, you get about 20 dB more, so a lot of gain with very little extra noise. So these are really awesome amplifiers. And what's amazing now is you can have them with gigahertz of bandwidth, so they work over a huge range, and they're just really awesome to work with. That's part of how you amplify the signal to actually measure it. Okay. Another thing that you can do with it is you can use the actual breaking of Cooper pairs to measure microwave photons themselves. So these are known as kinetic inductance microwave detectors. It's basically a superconductor here, and you make these little squiggly resonators, and a photon coming in will break a Cooper pair. That changes the inductance of the circuit a little bit, and that you can use to detect microwave microwave radiation. And people use these. Actually, a good friend of mine from grad school has a dilution refrigerator set up in the middle of the Atacama Desert. And they have detectors that measure the cosmic microwave It's actually crazy. It's just sitting in the desert. So the thing in my lab is just like out in the middle of the desert, and they measure the cosmic microwave background using these kind of detectors. On the qubit side, there's been a whole slew of different types of qubits where you basically have the capacitor,
Good, how are you?
Inductor, and these Josephson junctions, and you can play with all these different circuit elements to have this whole zoo of different superconducting circuits. I'm a little bit behind the time.
Good,
Can somebody mute him? Am I out of time?
Yeah, we're running out of time.
Okay. Well, let me just conclude. I didn't get to talk about any of the exciting stuff in my lab, but there's been a lot of progress over the last few years to make better and better devices. Before I was at Dartmouth here, I worked at IBM Research, where we're really taking this and running with it. So this is an industrial scale quantum circuit where you have multiple chips all sandwiched on top of each other, and you have all of these different chip layers with hundreds of qubits now that can all be entangled and in superposition states. This is kind of what it looks like at scale in terms of the circuit wiring, and there's numerous other startups and things like that. So while we can't have a Schrödinger cat, an actual cat be in a macroscopic quantum state, we can certainly make all of these be in whatever quantum state we want. Okay, so of course I spent too long talking about this, so I'll just go ahead and conclude. I was quite ambitious. I wanted to... So I'll just go ahead and end here. That macroscopic quantum coherence is really like the key ingredient used for these superconducting circuits. And superconducting circuits are one of the leading platforms for quantum computation, and it's really all thanks to this macroscopic behavior of superconductors and the nice properties of Josephson junctions. And then if you want to learn more about what were sort of the big challenges with the next decade or so of superconducting circuits, we can talk offline about these defects. And yeah, thanks for your attention. Thank you for hosting me. Too much time.